Welcome to CST 8149, Survey of Programming Languages. As the course outline suggests, we'll be studying three languages, C, Perl, and Perl TK. But for the first 4 lectures of this course, we'll be looking at the background of programming languages and gaining the tools to evaluate and compare them. Learning about programming languages is more than learning about their syntax. We want to have the tools to be able to analyze and decide which language is the best language for a particular task. To give us the background for this, we need to look at 4 questions in today's lecture. What is a computer? What is abstraction? What are programming languages? And finally, why take a course about programming languages? First of all, what is a computer? To answer this question effectively, we need to distinguish between special purpose and general purpose machines. A special purpose machine is a machine that has a small number of built-in complex operations. The user of a special purpose machine has direct access to these complex operations. An example of a special purpose machine would be a calculator. It has a limited task. The task is special purpose. The operations that it can perform are complex, and the user has direct access to these complex operations. A general-purpose machine has a small number of very simple built-in operations, but a programmer takes these simple operations and combines them in a meaningful way to provide the complex operations. And so built into the machine are only the simple instructions. The user can access what the programmer has provided, the complex operations, and the program simulates some special purpose machine. The advantage of a general purpose machine is that it can be programmed to simulate, to provide many different special purposes. And so what is a computer? A computer is a general purpose machine with some very simple built-in operations. Here are some of the simple built-in operations that we would find on a computer. Move, increment, sign, and repeat. In fact, these 4 simple operations can be combined to provide all of the functionality that we would want to use in programming an application on a computer. Let me show you how. We can take these 4 simple built-in operations and combine them to generate new operations. For example, we could take 2 of them, repeat and increment, and do the following. We could increment y and do the incrementing of y x times. What's being done here? Well, if we increment y x times, it's the same as adding x and y together. We've taken 2 of the built-in operations and we've generated a new operation using 2 that are built in. We can do the same with sign and increment. We could switch the sign of x, increment x, and then switch the sign back. What have we done? We have generated a new operation, decrement, using 2 of the built-in operations. Once we've developed these new operations, we would want to give them names. This will be the mechanism that the user of the new operations has to access the operations. For example, we can have add as a function call, or decrement. We now have a slightly more powerful machine that makes use of the new operations. However, the machine itself still only has 4 basic built-in operations. What is abstraction? We've seen an example of abstraction above. Abstraction is simply the hiding of complex details behind a simple form. The simple form is or are the names that we have added, and the complex details are the combination of the built-in basic operations of the machine. Let's look at some examples of abstraction. The first example we've already seen, add. As the user of add, I don't need to know about increment and repeat. Those details are hidden from me. I need only to know how to use add, pass in x and y. That's an example of abstraction. Add, is abstracting, is hiding the details of the increment and repeat. The same would be true of square root. When you study numerical analysis, you'll learn that square root is a complex operation. There are many steps involved in calculating the square root of y. However, those inner complexities are hidden from me. This is abstraction. I need only to know how to call the square root function, pass in y, and I can expect to be returned the square root of y. The equal sign is also an example of abstraction. The assignment of the result of square root to x involves some inner complexities. The looking up of the memory location, the storing of the value in that memory location, but all of those details are hidden from me. The equal sign is providing abstraction. This example here uses a C instruction, printf, a function call. And again, there are complexities that I don't need to worry about. Printf is provided in a library file. I don't need to know how it handles the display of the information on this standard out. I don't need to know how it stores the array A in memory, or the incrementing through of the pointer to find the object, the value, the integer at position 5. All of these details are hidden from me. And so printf is an example of abstraction. Abstraction is found not only in computer science, but even in normal spoken language. The following statement provides abstraction. The term queen. It hides all of the complexities, the details of the monarchy, and expresses one simple concept in a simple term, queen. The same is true of pregnant. There are inner complexities that I might not understand and how this has occurred. However, I can express it with one simple term, pregnant. This last example provides a tremendous amount of abstraction. We have a few symbols representing a tremendous complexity, an emotion. And so abstraction is the hiding of complex details behind some simple form. Understanding abstraction, what the term means, will be important as we study the languages in this course. Again, a computer has a small amount of primitive operations, a small set of primitive data types. However, we can use these by combining them to provide more complex operations, and these complex operations allow us to make our general purpose machine special purpose. Where does the abstraction take place? Well, that's where programming languages come into play. A programming language is actually the abstraction of complex combinations of the simple built-in operations of the machine and combining them in meaningful ways so that the programmer can use them to develop applications. In fact, the complexity involves both operations and data types. The operations and data types that are built into the machine can be combined to provide more complex operations and more complex data types. This is done when the programming language is developed. Later on in your course of study, you'll actually study compilers, and you'll learn how this is accomplished. However, in this course, we'll notice that languages provide abstraction by combining operations and data. Do different languages approach abstraction in different ways? Of course they do. Some languages look at abstraction and provide abstraction in different areas than other languages. For example, if we were to take a language such as HTML, we would notice that the abstraction, the details that are hidden from us, have to do with the display of information in a web browser, whereas a language such as C++ provides abstraction for object-oriented programming. And so different languages have emphasis or provide abstraction in different ways. Programming languages also allow the programmer to create procedural and data abstraction in varying degrees. For example, some languages allow you as the programmer to develop new data types and new procedures. This allows you as the programmer not only to use the abstraction provided by the language itself, but to add levels of abstraction by writing new functions and new procedures and developing your own data types. For example, object-oriented languages allow the user to add a great amount of procedural and data abstraction, whereas low-level languages allow the user less flexibility to add abstraction to the language. Why take a course about programming languages? There's 3 reasons. First of all, we want to develop the art of programming. It's possible to know the syntax of a language and know how to combine the syntax in the correct manner to make the program work. But the art of programming has to do with knowing the best way to use the syntax and to combine it to make the most efficient and effective code. To be able to program in this way requires us to understand how the language provides abstraction. How is the language hiding detail from us so that when we combine the details, when we combine the code of the language, we can, in the most effective way, use the syntax and provide efficient code. Reducing the learning curve. This course will involve learning 3 languages, but the more languages that you learn, the easier it becomes to learn new languages. Someone's made the analogy that learning a programming language is like learning to drive. Once you've learned to drive one type of vehicle, learning to drive a new type of vehicle is simpler. Learning C will be like learning to drive standard. You've already learned C++, it's like driving an automatic. And now as we move back to C, we'll see that there's some things that we have to do that we didn't need to do in C++ because it was done for us automatically. Learning Perl is like learning to ride a motorcycle. Powerful, fast, but there's some things that we'll need to learn above and beyond what we've learned already. Learning assembly language is like learning to build a car, and that will be the challenge of your professor as he teaches or she teaches you assembly language. To illustrate the fact that learning a language is easier once you've already studied one language, here's some code written in a language that you're not familiar with. Just glancing at it, you can likely figure out basically what's going on, based on your previous knowledge of programming languages. If you had never studied a programming language before, this new language would not make any sense to you. The third reason for studying programming languages is to be able to determine which language is the right language for a particular task. Take, for example, the code that you see in front of you. 5 lines of code. This is all the code that would be required in a language called Haskell to perform the quicksort algorithm. You can compare this with the code required in C++ to write the quicksort algorithm. What would take 5 lines in Haskell would take at least 30 lines in C++. And so you could say that there is one right language, or rather that there is one better language for the quicksort algorithm than another. If we were just comparing the number of lines, we would say that Haskell is a better language than C++ for writing the quicksort algorithm. But there would be other criteria that we would need to consider. Maybe you don't know Haskell, and so it would take you 3 months to learn it, as opposed to using a language you already know, such as C++. And so as we look at deciding which language is best, in a future lecture we'll have to look at the criteria for evaluating languages, and the purpose of that will be to determine which language is the best for a particular task. Where do we go from here? We want to look at, in the next coming 3 lectures, how can we decide which language is best for a task by looking at how languages have been traditionally classified, looking at how we can evaluate the individual features of the language, as well as looking at how different languages are implemented and the development environments that are provided.